Bradford, and today I'm going to be talking about problems with MySQL scalability. And in fact, my original presentation was this title, The Most Common Mistakes and How to Avoid Them. And after submitting, I spoke to Jason and I said, well, I really want to change the title so it's more proactive in terms of successful MySQL scalability. How do you build that from the ground up? However, today's presentation is more going to be problem, solution, resolution situations. But if you actually don't use MySQL right now and you want to know how to scale it successfully, there's a companion talk, which I'll mention again at the end of the session, called Successful MySQL Scalability, which takes the situation in reverse. However, for today, I'm going to run through 9 particular points which I find common from my time as consulting with MySQL. I have a background in database products for over 20 years, having worked with Ingress, Oracle, and MySQL. I've actually worked for MySQL in the company in consulting, and now do my own consulting. So I get to see problems every week. And quite often there are very simple problems that are seen and very simple solutions. So hopefully here, how many here actually are current MySQL users who feel like they've got a grasp of things? Hands. And how many are MySQL users that wish they had a grasp of things? Okay, all right, that's the other half. So that's good. That's the target audience. So let me start with a common problem that I see with clients, and that is my website seems to freeze or not respond. A common problem where the response that you're getting is unpredictable. And the cause of this is most likely very straightforward. And that is that MySQL is a database, is really unique because it has different ways of storing and retrieving data by the concept of a storage engine. Now this can be fine for people who come from a traditional background such as Oracle or SQL Server. And in MySQL, up until the current version, which is currently in beta, which ironically is owned by Oracle now, the default storage engine is MyISAM, which is a very fast storage engine for high write environment but low read environment, or high read environment and low write environment, but not great for a read-write environment. And the reason why is because it takes table level locks when you do any manipulation of data. And so the problem is that for any long-running statement, like an insert or an update or delete, they can actually hold locks. Or long-running queries, like running reports, also hold locks. And this is what gives you the unpredictable nature in terms of the website seems to perform or seems to hold up. The solution is actually 2 different approaches of the most common cases. The most important thing is to realize that you have to identify the cause of statements which are causing your queries to be blocked, i.e. the blocker. And alternatively, most clients, if they start with the default storage engine of MyISAM, realize that it includes a number of limitations such as non-transactional, no automatic recovery. And so by choosing a storage engine which supports an MVCC model, a concurrency model, and in the case of MySQL InnoDB, for example, which is row-level locking, you can overcome this problem almost immediately. However, that just addresses the locking issue, not actually the performance issue. And the goal here is really to tackle the performance problem. The most common situation that I see is not generally that write statements are taking a long time to execute. It's that read statements, which will take locks, read locks, they have to be completed before you can get an exclusive lock to perform a write. So if you have an end-user reporting tool or a developer that allows you to produce ad hoc queries, or someone who just does crazy things, then that can have a dramatic effect on a runtime system when you're expecting OLTP performance. So in this situation, it's important that you identify what the actual blocker is. And as I mentioned, MySQL is sort of unique in the way it stores and retrieves data. And in this situation, the default is not always the best. So stock standard installation, you have it installed, you will not even know that there may be options in case point of being able to address the storage engine. So how do we actually identify the cause of the problem, and how do we go working with addressing that? MySQL provides an ability for you to look at the SQL statements that are being executed in the system by a show process list command, or via the command line MySQL admin process list. And in this situation, what you see is you can see a list of running connections and threads that are in the database. And as a little example I've got there, what happens is that you have to you first identify the statements which are locked. These are the ones that are being blocked. And then once you've identified what is actually being blocked, you can then use the table or tables in question to then look for queries that are older than that statement by the time to identify what the blocker most likely is. There's no easy way to identify which statement is actually causing the locks in the case of MySQL, MyISAM. However, it requires a bit of investigative analysis to determine 1 versus 2. And this is obviously a very straightforward example, but you can see that I'm executing an update and subsequent selects are actually being blocked because of that update. And the converse can occur for long-running selects as well. So the solution is really to optimize those blocking statements. That should be your first priority, whether you're using a transactional engine or a non-transactional engine. There are various techniques that you can apply to that. Defining the correct indexes, having an appropriate query execution plan, perhaps limiting the query. Quite often queries can take a long time to execute. Maybe they're returning 10,000 rows or a larger network payload than is necessary, and you can reduce those. Quite often, queries that take a long time to run in the select situations are summary or aggregate queries, and by actually passing that off into a single queue or thread to produce data and summary data can overcome the issue of heavy select statements against very commonly executed tables that have a great change of data. And so just by knowing these things, you can actually change your application to support some level of data redundancy there. Or as I mentioned, the most likely case for most users is that they change the storage engine. I leave that point here is that that's generally a simple solution. However, that comes with certain caveats. And I'm not going to discuss the caveats, but using MySQL between MyISAM and InnoDB, the caveats are, for example, if you use full text, that's not supported in InnoDB. InnoDB has to be configured differently in terms of its memory buffers, and its disk footprint is generally 2 to 3 times larger. So changing can be a good thing, but can have several ramifications. One of the next most common things I see is, why is my database so large? And you may wonder, well, what's the relevance of the database being so large? What's the footprint? But that comes down to generally the size of the system that you have in place, the time it takes to do backups, and particularly the time it takes to do recovery. And the most common problem with this is people shove stuff in the database that shouldn't really be in the database in the first place. I've seen systems with high volumes of data, cases where 80% of the data is static data that's being stored in the database, or PDF documents, or large chunks of uncompressed data that could be compressed. Now, there seems to be some debate that goes back and forwards that I want to put everything in the database because I want to back up the database and I want my data to be consistent. That may be a novel approach to be able to solve your backup and recovery problem. However, with MySQL, anything that's stored in the database is used internally inside the MySQL kernel. So the issue that you have when you store large objects in the database is you actually affect the memory that's being used within the individual session buffers or in the global buffers that MySQL have for other types of transactions. So it's very important that you manage that memory well. MySQL is an unbounded process, so if you misconfigure your environment and you have too many threads doing too many things taking too long, then you can actually get in a situation where you can run out of memory. So it's important that, unlike an Oracle environment where you can segment off certain particular storage implementations to not affect your global areas and your process areas, in MySQL you don't have that choice. So if you're reading in a lot of blob data, then those data pages are being loaded into memory. For example, the InnoDB buffer pool size, they're being massaged by independent buffer sizes, and that memory is all being taken away from putting more important data into memory so that those queries can be accessible more quickly. If something's a static file, then serve it from a static file server. The other thing that's important is that the size of your database and your type of recovery process can depend how long it takes to recover your system. So while you may consider having everything in one place being a good option for backups, most people forget to realize that a recovery time is just as important as a backup time. Again, the solution to this problem is really quite simple. There are lots of cases where you can compress data in MySQL columns, particularly data that doesn't have any indexes on it and is not searchable. If those criteria exist in place, well, then there's no need for the data to actually be uncompressed. You can compress it at the database level, or more optimally, you can compress it at your middle tier, your web server level, so that the database doesn't actually have to work on that. The impact here is you have more CPU cycles, but if you can push those CPU cycles out into a load-balanced environment of web servers, then you're giving the database more time to focus on what it has to do. And obviously taking static files and moving them out of the database and having reference to files can certainly avoid the overhead of managing those things. This is one of the most popular queries that I use, common queries, when I come into a MySQL environment. I look at the overall size of the environment, and then I can drill down to the overall size of tables within every individual schema. And under most environments, you find 2 or 3 tables which take up 60, 70, 80% of the database. And that's obviously can be your focus. And sometimes it can be very easy just to identify something that may or may not require some level of coding changes, but can certainly reduce everything and ultimately provide greater performance and scalability. So another common problem is that people say they can't access their website. It's a common problem. And here's actually a true story from a customer. I asked this question: how do you know when your server is not available? And their answer was, well, the users will tell us. This is not a good practice to have if you want to remain in business. You'd be surprised how many people do not have monitoring in place. And I know Theo was just talking about monitoring, and it's something that I'm pretty adamant that needs to be in place from day one. And I actually have another slide on that. And the comment of monitoring and unmonitoring server can give you payback immediately is also very true. So unfortunately, just monitoring a system is not sufficient. There are several levels and classifications of monitoring you have to put in place. And alerting obviously is something that can alert you when certain thresholds are exceeded. These two systems are basically reactive. Actually, I have that on the next slide, so let me go to the next slide. Monitoring and alerting are great because they're a graphical interface. You need to have them in place. They're good for being able to spot things visually. They're great for trending things historically. But they're really useless for real-time analysis. If you're doing monitoring of a system, for example, every minute, and something happens every 5 seconds that causes the system unavailable, you want to wait a minute or 5 minutes to be paged that the server is in some level of stress or the server is unavailable. You really need to know what's happening straight away. The other thing that's interesting about monitoring is most monitoring servers only monitor what you've configured it to monitor. And in MySQL, there are hundreds of variables that you can monitor, and you can't get that data back after you've lost it. After the point in time, it's lost. So it's really important to consider that with monitoring. You monitor everything that's available, you collect it. You may not present it graphically, but you may find a problem in 2 months' time where a certain particular lock weight variable you're looking at is causing a problem, and you might want to go, well, I want to go back in time and see whether this is a new problem or has been a recurring problem. Was it a problem on a previous version of MySQL that since you've upgraded? So it's very important that you take the time to actually invest into making sure that you can gather everything that you want. Most solutions that I advocate to clients is that you have a dashboard in place. Simple dashboard is a single page that provides traffic light analysis of whether is everything okay, whether there are some warnings or some error, and you sample at very frequent times. And the equation I use is 0.1% or 1 in 1,000 transactions. The benefit of this is that you can see what's happening on your system as a primary triage method to be able to identify what problems you have in the system. You can identify problems long before even the users can notify them, and you can also then look at potential ways of being able to look into resolving these things. From a database perspective, I don't have it on this slide, but I have it on some other slides. I have some screenshots. From a database perspective, you monitor things like the uptime to the server for load, the latency time to connect, although that TCP has an overhead on that, the number of database connections you have, what's locked, what's not locked, what's active, what's passive, what replication delay is. And if you have all those numbers on one screen across all your servers, combined with other things like, for example, your web server states how many Apache connections you have, how long your page is taking to load, how big your page is. If you see all those things on one page, it's amazing what you can see when a problem actually occurs. Of course, as you scale, from tens to hundreds to 6,000 servers, for example, you can't monitor everything on one page. You need to move to a more of a heat map environment where you identify just problems. But the dashboard is really important to get started. The dashboard, like monitoring, is almost a black box. They monitor effectively end-to-end of what can occur. What's really important is that your application supports a level of instrumentation so that you can drill down into where problems may be. Because while it's important for the business to know what KPIs you want to have in place, you need to have something that may be able to drill down into a particular problem inside an entire transaction. And obviously that needs to be implemented so that you can enable or disable or adjust and extend in real time. What you'll probably realise now is that people have front-facing status websites, which are dashboards like Twitter or Amazon Web Services or SmugMug, for example. And they tell you what's actually happening on their system. So that's a public-facing version of the dashboard that you have in place. And a status site is something that enables you to be able to communicate with your clients of whether things are problems, whether they're up or down, allow for clients to give feedback. And the most important thing for people I've even seen that do this is don't host it in the same environment that you host your servers. Because when something's down, you want to be able to notify people, and I've seen people that do this, and it's really good where we want to notify our users that our site's down, but our notification site is also down. So it defeats the point. Successful scalability comes from having that level of redundancy in place. MySQL generally is not a single server. Most working environments will have more than one MySQL environment configured by a MySQL replication, which is very easy to support things like read scalability, good for having backups, good for moving towards a failover, a high availability environment. And the greatest problem with replication is that replication cannot keep up with the load. Replication is an asynchronous process, so writes are happening on the master and then they're being replayed on the slave. So, as with all things, you need to understand what replication does, how it does it, and identify the weakest link so that you can identify that as the threshold you need to work with. The threshold is not that you can do 3,000, 4,000, 5,000 transactions per second on the master. The threshold is how many you can replay on the slave. Because if the slave can't keep up, then your replication is useless. The data is out of date, the data is inconsistent, as we've just heard this morning, and in some situations that data is then trash. So identifying the weakest link is important, and obviously don't exceed that, or there are in fact a few ways to cheat, and I'll discuss a few of those as well. So, as I just mentioned, if replication can't keep up, then it's useless. People use replication for backups, so if your backups aren't consistent, then how are you going to do point-in-time recovery, and then how's it going to affect your business? So, from a slide perspective, and you can do this in diagrams, so sometimes it's good to actually spell them out so that you can actually see the order of things. On the master, there are four primary things that occur when you apply a change to data, insert, update, or delete. The data is written to the data either in memory or on disk. With IMDb, it's written to a redo log to support durability. The statement is written to MySQL's binary log, which is for other people effectively an archive redo log. And then an OK return is returned to the client from a commit perspective. On the slave, however, a lot more occurs. The slave has to detect that there's been a change. MySQL slave process is a pull process, it's not a push process. So the slaves will detect a change has occurred, certainly in microseconds. It has to then retrieve that information from the master to the slave, so there's network latency involved. It then writes it to its own disk-based log file on the slave machine, which is known as the I/O thread. Then the I/O thread data is actually read from disk again, and then applied to the database via the SQL thread. And then, as I just mentioned for the master, a similar thing occurs, that data has to be written. That application of that statement on the slave is the slowest, weakest link in the system. And the reason why is because it's a single thread. On a master environment, you have multiple threads writing to the database if you're using a transactional environment. On the slave, everything is replayed in a single thread. So if something took 5 seconds to update on the master, and in the meantime 300 other statements updated other data, on the slave, those 300 statements don't occur at the same time as that 5-second update. It happens in a sequential mode. So as I talked before about identifying blocking statements, not only is it slow for performance, but it's also slow in the replication model. And just for reference, the second slowest, weakest link is the actual writing of data on the slave. The reading and writing of disk. The disk I/O is generally the bottleneck. So MySQL provides a number of ways to work around this. A replicated slave, if not used for a backup process, does not have to be configured identically the same as the master. Your table structures can be different. You can restrict or ignore data that can be applied to a particular slave. You can use different storage engines in place, or one thing that I found, particularly for larger scale environments, people use different index implementations on their slaves, even to having different slaves having different indexes on different indexes on the same table and directing queries to those things for optimal performance. However, when you find that that still doesn't work and you need to look at something else, there are some clever ways to get around that problem. Google is a good example in their AdWords and AdSense where they run their environments with RAID 0. So they're getting additional disk throughput by being able to increase that throughput on their slave. Another idea which actually came from Pultuckfield from YouTube was that that SQL thread is replaying transactions that it knows about because they exist in the redo log and they exist in the master's binary log. So you can actually predict the future of what's going to happen, and by having separate threads you can pre-read that data in a different thread, so at least it's been read off from disk and put into the disk buffer, put into the memory buffers, so the time to execute the query can be reduced, sometimes by half. So these are ways to actually circumvent the normal replication process to speed up what's happening. Everyone still awake? Feel free, if you have any questions during the talk, feel free to grab me at this point in time the slide and we can discuss them at the same time. Okay, so I have had to solve more than one disaster in my past. And what happens when you have effectively a hard drive failure? Having a physical equipment failure is one problem of downtime, but having a hard drive failure is obviously more important for your data. And again, a question that I'll generally ask clients, and this is an actual client example where I've asked for, have you perform a database recovery? And they said no. And I said, are you aware that the backup that you do at night is really is a static backup copy, and all those transactions that are happening during the day, those multi-million-dollar sales with Ford, which was their largest client, do you know that those transactions are lost if you have a failure during the day? And they weren't aware of that. They weren't aware that backup strategy only provided a static recovery, not a point-in-time recovery. And so this leads to the important mention in MySQL that you have to have a disaster recovery plan in place. Now, with MySQL, point-in-time recovery comes from the binary log, and if you use replication, then you automatically have it enabled. But if you have a single master server, you may not have it enabled. It's very important that you know it. This slide, everyone in the room should know about it, so I shouldn't have to repeat it, but I have to repeat it every single time I see somebody who's paying me to tell them what they need to fix, so it's obviously relevant to here. You need to test it, you need to time it, and you need to verify from end to end. I've had several clients that don't verify their backup strategy, or they'll actually test their backup strategy before production on a database that has no data in it and no load. And yet when they have a database that's, 300 gigabytes and they have 5,000 current connection users in the system, they don't realize it actually takes an hour for the system to go through automatic recovery mode to redo transactions. So it's very important that you're aware of those things. Now, for the entry-level person, some time ago, I actually created a backup recovery quiz where I see this problem every single client I go to, and sometimes I just feel like, okay, read this first. And you can go to that link. I'm not going to go through the points, but just very quickly, that will be included in my slides that I'll publish. These are the 10 points in place, and it's amazing that I can have clients who get like 2 or 3 or 4. And if your data is important to you, if that's your business, if you're not bricks and mortar, then you really should be worried about that. And really, I don't know how many people in the audience are very technical, like from a technical perspective, but this should be something that scares the CEO at night. Will my business survive? And I've seen a $100 million business almost go out of business overnight because their very expensive SAN dropped 160 mount points and trashed 60 database servers. So it's important that you test these things. Moving right along. I'm actually ahead of schedule, which is good. This is also a common problem that I see. the database is running an excessive number of queries per second. In this case, it was, in this particular client, it was 1,200 queries per second, and they only had a small number of users connected to the server. I mean, at 50 users, that equates to 60 queries per user. Is that really how many queries you're doing on the database on a per user basis? A common problem, which people don't realize, that there is also an approach that you should be looking at solving that problem, and that is determining what queries are running and, more importantly, why they are running. The reason why is because, and I find this is a common problem, and I have several examples to show you, is that most applications run an excessive number of SQL statements. And if you want to scale your system, that comes from having more availability of the resources to actually process more queries. So if you can reduce the number of queries that are being executed, therefore you have greater scalability. And quite often I see environments where they're duplicate or redundant, or particular queries that can be cached. And another example, which is referred to row-at-a-time processing, it's very common from the historical inventory processing days, where you process one row at a time when you really should be processing a chunk of data, and it's a rat versus a cat process. I mean, the goal here is we want to reduce the SQL load, so therefore the MySQL kernel can support greater load in the future, and that will obviously give you greater capacity. If your servers are running at capacity now, if you can make a reduction of 20% of queries, then all of a sudden you can see that you can then focus on more important things. Let me give you a few examples just to sort of highlight what I mean. This one is actually WordPress, which is a very common product that's out there for those hosting providers that are in the audience. How many people host? How many people go, I hate WordPress and a WordPress MU with 10,000 tables because they want to create 100 users, and that just drains your entire dedicated server environment. Here's a good example where they run a whole pile of queries. This is row-at-a-time processing. You're very happy that, WordPress is great. I use it. A lot of environments just don't use WordPress MU because the poor old hosting providers cringe. But this is an example of even a popular product suffering from a common issue, and that is row-at-a-time processing. That is, you're executing a query against the database, you're returning the results to the server, and then executing another query. Now, in a well-tuned system, the most time it takes to execute an SQL statement is network latency. The second most time is the network packet overhead of how much data you're returning on the network. Quite often the query itself is actually the shortest period of time. So in this example, those 8 or 10 queries that are running, the most amount of time for those queries is the time it takes to connect from the application server to the database server and in return. Here's another example of a client that had a similar situation. Again, we're using row-at-a-time processing, and the solution is very simple. The query below shows a chunk-at-a-time process, where you determine ahead of time what you want to query, and you make one SQL statement. And this can actually reduce the time it took to do this, literally, by 4x or 5x. It's as simple as that. Here's another classic example that I see with clients. People don't actually have a look at what statements execute on their page. And if you're a developer, you should look at every SQL statement that is being logged on your pages when you load them. You really should have that as a tile on another window. Here's a client that actually executed 9 queries against the table, 7 queries which were full table scans, and they really only wanted 2 rows. So there were actually multiple bugs in their layer, their decoupled layer for data work, database. And every one of those queries is returning a huge payload of data, in this case like 200,000 rows, back down to the web server, and then executing it again. And even though the database might be more in tune to be able to cache that at like the query cache level or something, the actual network overhead is killing you. And the time to load the page is actually reduced by 500 to 1,000% just by looking at the statements that should not have been run. This is a good case of redundancy. Here's an even better case of redundancy. Here's a particular query. The sampling time was listed there. Over 5 minutes, there were 6,000 executes of this query. And what was really interesting was it's being executed from a table using a primary key, which is auto increment. Auto increment doesn't by default store value of 0. So a simple client boundary condition could exclude the actual even execution of the statement. The statement is completely redundant because it always returns 0 rows. So quite often, just looking at the SQL statement is not enough. You have to look at the data and you have to look at the reason why the SQL statement is being executed. Because when people come to tune SQL, quite often people don't realize that the most effective way to tune SQL statements is actually to eliminate it. That should be your first goal. The first goal shouldn't be to make it faster. The first goal would be, do we need to run this SQL statement? It's a different mindset. So how do we do that? You need to capture and analyze. Capturing DML statements is easy. Capturing select statements is harder. Yes, I actually have a list there. Sorry, I don't have the slides on my screen. So I gave a presentation a few months ago which more details the capturing, analyzing, and optimizing particular queries. For those people radically scribbling this down, my slides will be available afterwards, so don't feel too bad. You can still write it down though, don't stop. So when you want to catch DML statements, MySQL, using the binary log as I talked about earlier, writes every transaction. There are several tools. You can look at that binary log by the MySQL bin log tool, but there are several tools, including the market tool, or I even have a one-line statement which can give you an aggregated result of what's happening. And quite often this can be even interesting because you can see a load. You might see something that's like 50,000 statements as opposed to the next one which is 10,000 statements. And that 50,000 statements is something silly like a messaging queue where it's doing a high amount of reads and writes. And those messaging queues are bogging down your primary server, they're polluting the binary log file, they're slowing down the replication on the slaves, and that might be a good example to be able to partition that off into a separate instance. So just by looking at those top-running queries, you might be surprised what you see. And correspondingly, you'd want to look at that over a period of time because loads will obviously change during the day. To capture select statements, this is harder. There are ways to capture sampling processes by the process list, but I mentioned that captures queries in the active execution or queries that are slow. If you enable the MySQL general query log, which you should never do in production, if you do that in production, you should, go wash yourself. Because once your disk is full, then you realize that your application doesn't work because your binary logs aren't being written and your entire environment is trash. However, if you're a developer or even in a simple testing environment, a general log should be always turned on. The general log should be analyzed to see what queries are being executed on a frequent basis. A developer should be seeing all those queries. When you read a page, you really want to know what's happening behind the scenes. You need to take responsibility to protect the data and the systems that you're working on, not just writing code. So it does have a certain purpose. The best way actually on a client-server environment is to actually catch the TCP packets in the act over the MySQL protocol. And there are several tools, including a market tool which I use extensively, basically every client, where I can see what's running on the database server. And unless it's too many packets that are actually being dropped at the TCP stack level for processing, you can generally see what's happening in the database at a point in time. How many queries are happening over a second or 2 seconds or 3 seconds. And that can really highlight queries which are either redundant queries or queries that you should be caching in some way. Queries where you're selecting information from company tables and you're doing that every single page, that primary information is very static and rarely changes. So you should be able to pull that into some level of caching. Or other queries where maybe you should have a different type of caching implementation in place, like the topmost views videos of your website. That doesn't have to change every second. That can afford to be run in a queue and change every minute or every 5 minutes. The other option is to use applications. There are a lot of frameworks now, like a Drupal or Cold Fusion or other environments like that, will actually log all the SQL statements for you, and they'll actually give you timings, and they can be quite helpful. I think I actually mentioned that on a previous slide, but I'm not going to detail here how to capture that. We tried to actually do it at a 90-minute talk. It really is like a 3-hour presentation just to look at SQL statements, but there is good material there. I will say that this is the most important tip that if you're a developer in the audience or you're a DBA in the audience, you should take away on this particular point. And that is every SQL statement should have a comment in it. After the first word, after select or insert or update delete, you should use C-style comments and put some level of reference there. You shouldn't try to be verbose, you should be concise, but enough information to identify where that query is coming from. The reason is, as the number of developers increase and as the volume of queries increase, you want a DBA to know what the cause of the problem is without having to either talk to a developer or log a request form to ask a developer to look at code and then for them to get through the code. You want to be able to say, okay, this code, which is ABC or some description, here's the query that's being executed, and you might need to then be able to tell them how to fix it. So it's a very simple way to be able to improve the communication channel and reduce the time to actually go through that support process of optimizing queries. Moving right along, I have clients that will come to me and say, my database is slow. It takes 5 seconds to load my page. And it is true. You pull up their page and you look at it in Firebug and it takes 5 seconds to load. The problem is that you need to evaluate what is actually taking all the time of your environment. And that includes a level of instrumentation that sometimes you cannot gather without actually embedding that into the application. Unfortunately, on websites, we have fantastic tools to do that, where we can actually break down the payload of a web page and find out what's going on. And in this particular client case, their page did take 5 seconds to load, so they weren't very happy about it. But their HTML content took 400 milliseconds to load. So I said, sure, I can tune 8% of your system. So as a database expert, my charter should be to make sure that I improve the performance of the system regardless. And I have become more and more adept of knowing not just tuning at a database level or an operating system level, like for example changing the IO scheduler, or at an Apache configuration level, but looking at how to look up and down the stack. So here, if you're a developer or a DBA in any regards or a support person, it's important that you identify where a problem actually is. So the performance is the only thing that's important to the end user. All they care about is that the system is actually giving them back what they want. And the reality is that performance, people will never be happy. So it's always a matter of perception to determine what is actually defined for performance and what is acceptable. And this has nothing to do with MySQL. This point has nothing to do with the database. It has everything to do with accessing the data in the database and realizing that sometimes you can make huge performance improvements by just knowing what's actually being involved. And generally, there's a whole slew of tools that you can use to actually look at what's happening, identify down into a small instrumentation level what's really happening with the database volume. There are some public tools that are available there that I've listed. But really, the best tool is to actually just get the HTML page directly via a command line tool. And on my dashboard examples, generally what I do is I do that. I actually get the HTML page or several versions of it. I will record how long it took to get the page and how big the page is, because I've seen people that get an 85K homepage and they have http://www.domain name/images/xyz/image name for 80 assets. So you can actually reduce 15% of the HTML content just by removing the redundant domain name in front of every image. It sounds really trivial, and it might sound like, okay, well, what's that actually going to give me? Well, that 15% is a faster download of that file, and if you understand the HTTP protocol, that means it's faster to get the next series of assets, and also the socket that's being opened on the web server is now open less, so therefore you can support more queries, more requests. So little things make a big difference, and just monitoring those things are very important because you can also see if there's going to be extra overhead. Those things should be into your monitoring systems. And obviously writing code should be important to instrument what's happening inside. There are two references that I use quite a lot, and I usually give several tips, but I don't claim to say these are specific improvements I can show you. But Steve has a number of books on terms of high-performance websites, and Yahoo has like 43 points of improving HTML performance. And some of those performance tips are really quite trivial. The simplest one is to take all images that are coming from either your domain or a subdomain and breaking that across 3 CNAMEs. And that's as simple as just making a configuration change and in your code splitting images between 1, 2, and 3. When you understand the protocol, you can understand things can be loaded faster. And there are other ways in terms of improving caching and so forth. So I would definitely recommend that even though we're talking about MySQL, you need to be aware of these things. Because you can improve the performance of the database. by the perception of saying the website loads faster. However, the greatest problem, or the second greatest problem, that I see is that people determine that they have a system in place and that they determine that we need to grow and scale, and so therefore we have to add new hardware to the system. And I want to be able to support this. What's actually involved? So your goal and objective, I guess I call it solution, maybe it should be said goal, but your goal is to develop an approach which is seamless and unattended effectively for a human to be able to deploy servers into your architecture other than they've just been plugged into a power network. I've worked on several environments where, even at 100 database servers, they still do things manually, which is just crazy. Facebook that has 6,000 database servers, no human touches what's going to be installed on a system. They just physically don't have the resources to do those things. So how do you develop a solution for that? Well, as I've mentioned, integrated monitoring is actually the key. It should be done from day one. Never is. People never implement monitoring well enough. It's always an afterthought. And if you actually do it from day one, if it becomes part of your methodology, you'll actually realize how benefit is, and you'll wonder why you never actually had it in place. You should actually, the level of extent should be, monitoring should be installed and configured on the server, and as soon as that server is identified, for example, a database server, it has database monitoring which is failing because the software hasn't even been installed. And so it moves to that sort of like test-driven approach that you'd find in an agile environment where you're effectively writing the test case first. Your monitoring is a level of system testing. Automated deployment comes from very simple things. Who here in the room does not know what version control is? Nobody. One person. Game. Who here does not use version control, even like in a single user environment? No one's game. You'd be surprised how many people don't use version control. And hopefully everyone in the room here actually comes from a structured environment, so you understand the concept. But it's essential in terms of being able to create build and release, to be able to do automated, reproducible installations of your software. And it's important that you will have a separate system, a chef or something related to manage runtime configuration and production. The greatest sin is to put a configuration file into your deployment. I've seen clients that put their connection strings for connector J into their raw file, which they deploy on the production server. And when I said, well, we need to tweak these couple of configuration settings, can we just put that in your properties file? They couldn't do that. They had to actually build a new version of the software, deploy it to the production server, and restart their web server just to make a change to connections. You should never do that. That defeats the purpose of being scalable. Ultimately, the goal here is to move to an environment that as soon as the system is available for use in your architecture of a certain classification, it's under an automatic discovery mode. There's a controller that goes, I have a queue of, I need a database server over here, I need a web server here. As soon as something comes on board, it's smart enough to actually know. It's a nice utopia environment, but it's actually not that hard to implement. From a coding perspective, there are three things that you need to do. The first thing is you need an API. If you don't have an API in place, then that's going to kill you in the end. I've seen clients that have an API in place and then also have different code for the OLTP and different code for their batch processes. So three separate pieces of code that are implementing business functionality. It's just designed to fail. The biggest thing about having an API is that if it's on a particular protocol, HTTP or RPC or whatever, it really enables you to test your software. And testing is all about testing the software to failure. If you want to scale, you need to be proactive. You need to be preemptive of knowing what's going on in your server. You need to know what's going to happen ahead of time. How many people here have seen the Twitter fail whale? See, everyone's going to put their hand up now. Okay. So the people that are too lazy haven't seen it. Twitter has this fail whale, and it's frustrating. People find it frustrating. But it's actually not really frustrating. It's actually very clever, because the failed whale is something that returns very quickly, like, for example, in less than a second. The new dig, for example, is woeful. I actually have screen prints in my other presentation where it waits 5 seconds when it times out and actually tells you on the screen, I waited 5 seconds. The failed whale is a preemptive approach where the system is knowing it's getting to its capacity and starts failing early. That means that the servers aren't keeping sockets over, they're not getting this reciprocal rolling stone effect. And whilst annoying the users, it's annoying a small portion of users, and generally you hit reload, and unless they have a serious problem, then your tweet goes through. You don't know how to do that unless you have monitoring in place, unless you test your system to failure. And by doing that, you can be more proactive in your scalability rather than reactive. There are two other things from a coding perspective that you need to be aware of, and these are more architectural and actually more relevant for my other presentation, but in terms of identifying the common problems that I find with people with scalability, I solve the performance problems, which are the tip of the iceberg. Underneath the water, there are architectural problems which will always limit you in actually growing and scaling. Data has to be available at different levels for different purposes, and there are actually 4 levels of data access, at least 4 levels in this case, where you can read and write your data, you can just read your data. The data's not actually available at all, or you can get the data from a cache. A good example is if you have a large website and you want to take off the user management offline to do some maintenance, which is a highly available environment you need, you may be able to use a read-only environment. So people can still log in, but people can't change their preferences, or new users can't sign up for a short period of time. You can disable those options on the website. Your website is still available. Your website is still serving pages. Your website's not down because one component needs a level of maintenance. So you need to design potentially a messaging system that can notify you what data is available at a table level or at a particular class of objects, or even a series of rows. And this can be very good if you want to do things like rebalancing in a much larger environment. The other thing that you have to consider is that there are at least 3 different ways to scale your application. There's read scalability, write scalability, and caching. And again, these are important because your architectural requirements will differ in those. In MySQL, read scalability is generally the domain of replication. Replication is almost trivial to implement and difficult to put into the code unless you've already configured your server to handle write connections and read connections. Adding a load balancer to read connections is quite straightforward, but if your application early products like WordPress, I don't even know if WordPress still does it, but Drupal and these other ones, they never actually had the support of being able to write with one connection and read from other connections. So they were limited in this way. Write scalability is much more complex, and generally this is the domain of making code changes, being able to support sharding, being able to have some partition model in place so that you can segregate your data. There are other products that are coming in place now that look and feel like MySQL, that talk the MySQL protocol. They integrate into the LAMP stack, they use the connectors, and do the scalability and sharding behind the scenes. So there are a number of sort of products that are coming up in that area. And people should never discount the benefit of caching. Caching should be at multiple levels. Caching should be potentially at the database level at the query cache if it's of benefit. In the application, maybe storing the results of the query, or storing objects as they grow over time, using a lazy instantiation. I really hate ORMs like Ruby on Rails and Hibernate because they want to retrieve the entire object with lots of joins, and 9 times out of 10 it's completely redundant. That level of lazy instantiation is really necessary. Or another level is a case on a media site where they were doing all these queries and we took a front load page time of 600 milliseconds down to 60 milliseconds. 10x improvement. In some of those cases we're caching certain chunks of data, like the most popular queries, particular categories, and physically writing that as HTML or an NFS petition so those pages can be served up, and that only has to change in over a certain period of time in a batch process, rather than being executed in theory by every particular person. So caching can happen at different levels, including the application. So, what is the number one problem that I see when clients approach me? They just say, my website is slow. They cannot give me any more information than my website is slow. So my advice is seek professional advice. If you can't tell me any more than that, then you are really in trouble. So hire me or talk to me and I'll recommend other people to do with that. As I mentioned, I've worked in databases for quite some time. I've worked at Oracle, I've worked at MySQL, I do independent consulting now. Those are my details, which I'll have up later. But just to recap, because we're running close on our time, I won't take any questions. I find that monitoring is the most important thing you have to put in place. People don't do it. If you don't have it in place, you should do it. because it's very important to be able to predict and preempt what's happening, and for scalability, that is essential. If you don't know what's going to happen before it happens, then everything is reactive rather than proactive. You need to choose the best products. I guess I didn't drill down on this as much, but sometimes MySQL is not the best product for what you're working with. Sometimes, storing objects, for example, should be stored in the file system, or session management should be stored in a key value NoSQL type product. There are always different ways to do things. Don't try and force MySQL to do everything sometimes. The best SQL statement, you should never have to actually run it. I talked briefly, unfortunately I could spend an entire hour talking about how you'd implement important accesses for data access and in terms of scalability. And you should always operate below a critical point, because what most people, and in the audience here I would ask, how many times have you done a database recovery of your system? 90% of people will not put up their hand, and the other 10% will probably be ashamed because it didn't work as planned. You never actually want to get your system to failure. You want to be able to get to a point where the system can self-heal or self-recover, because recovery for a failure is very difficult. I think I added a few more points, but there are things we haven't talked about, like timing out pages and aggregated results. I mentioned successful MySQL scalability, something I spoke about a few weeks ago. It's the same principles, but discussed from the ground up. So if you don't have an environment in place now and you want to make sure it's successfully scalable, then you follow this process. And as I said last time, we give a money-back guarantee that it works. You never paid me anything, so it's not going to be worth much. But if you apply these things, it will really help you to be actually architect something that will massively grow and scale. Because that's really what you want to be able to do. You don't want to be able to take your system and double it or triple it. You want to have 10x or 100x performance improvements. And it's an iterative approach. One solution doesn't solve all problems. And large organizations, eBay is a good example. They've gone through this entire re-architecture 3 or 4 times. Last year or 2 years ago, implementing MySQL, which was a great thing. So there are my details. No one's actually asked any questions. We have some time for questions. Yes? No. Okay, so the question was, will you use MySQL for centralized logging? No. You may use you could use it, but you would definitely separate it from your OLTP. You have it in a totally separate environment because you don't want that to clog your traffic. So for logging, it could be okay if separated, but then it's a matter of how do you partition it, how do you archive it, and then what access paths. And that would determine whether you want to use MySQL or a more practical NoSQL solution. No, yes? Yes. So there are some products behind the scene. One that's sort of been stealth a little bit, but that has a lot of promise, is from Akiban, A-K-I-B-A-N, out of Boston. And they actually thrive on the system the queries being more complicated, and will do automatically sharding underneath the scenes. There's another product which was called Clusterix, which has sort of been in stealth for years. There are people who try to do this at an abstract level, like either via MySQL proxy. There's a product called DB Shards. These all things seem to provide some level of support and some level of implementation, but it's a matter of identifying with your environment whether it can actually support all your needs. And quite often, the cases that try to do it under the scenes may not handle all those particular cases. There's greater promise with the ones that just sort of use MySQL and go from there. And there's probably a few more if I thought about it for a moment longer. Yes? Okay, so the question was, what about MySQL monitoring? If you actually, can I do the web here? I was asked this question a week ago. And so the answer starts with first identifying what monitoring products are in fact available. Here's a website called Monitoring MySQL, which attempts to list things including types of products. There are a lot of products out there. The categories fall into open source, free versus subscription. MySQL Enterprise Monitor is a tool that's provided from MySQL on the support agreement. If you have no monitoring in place and you want support, it's a great place to start because it's better than nothing. If you have nothing in place right now and you need monitoring immediately, the quickest product to install is Monyog. Takes like 3 minutes to install. It is unfortunately commercial, but is well priced, and you can use it for 30 days without actually doing anything. The most popular is definitely Cacti and MySQL Cacti, the customized Cacti templates, which I now think are called something other than MySQL as well. That's the most used product, and it's generally the most flexible. Does that answer your question? But there's a few more that list there. It's generally it comes down to whatever your system administrators have in place and are more comfortable with, try and work with that. But if you have no monitoring in place now, go put on Monyog and you'll actually just see what's happening. It's a little inflexible in extensibility, but it's better than nothing. You get it for 30 days. Yes? Yes, it's Monyog. So if you actually go to the company's WebYog, and they have a software product called Mon, M-O-N-Y-O-G. All right, we'll wrap up there. If you have any further questions, please feel free to come and grab me quickly. I'm actually leaving on a plane very soon. Thank you.